Hello, welcome to a new lesson. Today we are going to see what is the shape of the derivative of a function of a complex variable, but in terms of polar coordinates. So we are going to suppose that the function of complex variable z is f of z equal to a function, but now instead of Cartesian coordinates, we are going to use r and theta, right? And then plus I b of r and theta. So we want to see what is the derivative of f with respect to z, but in terms of the polar coordinates. Okay, so first of all, we need to take the derivative. And looking at, we have two functions of two variables over here. We are going to have to use the chain rule, right? Because we are going to consider that r and theta are functions of z and z conjugate, right? So this means that, for example, we know that r is equal to the square root of x squared plus y squared. But we know that, if z is equal to x plus iy, then we know that z times c conjugate is equal to x squared plus y squared, right? So this means that actually r is a function of z and z conjugate. So this is telling us that r is equal to the square root of z times c conjugate. Okay, so we can do the same with theta, right? We know that theta is equal to the inverse tangent of y divided by x. Or no, actually, let me do it other way. We are going to say that z in its polar form is equal to r e I theta, right? I think it is easier to solve this for theta to get a function of the variable z, right? So from here we can see that c divided by r is equal to e I theta. And then if we take the natural log on both sides, we get that the natural log of z divided by r is equal to I theta. Okay, and so from here we get that theta is equal to negative I, the natural log of z divided by r. Okay, perfect. So again, we are going to consider this expression to calculate the derivative of f with respect to z. Okay? So looking that we have functions of r and theta, and that r and theta are functions of z, we need to use the chain rule, right? So for example, for the u, we will get that this is the derivative of u with respect to r, and then the derivative of r with respect to z, plus the derivative of u with respect to theta, the derivative of theta with respect to z, and then plus I times the derivative of b with respect to r, the derivative of r with respect to z, plus the derivative of b with respect to theta, times the derivative of theta with respect to z. Okay, so as you can see, we need to calculate the derivatives of r and theta with respect to z, right? But we already know what are the expressions of theta and r in terms of z, so I think that is not too much problem. So for example, for theta, we have that the derivative of theta with respect to z is equal to minus I. And then, looking that we have a natural log, you know that the derivative of a natural log is, the derivative of the argument divided by the argument, right? I mean, the same function. So this will be the derivative with respect to z of z divided by r divided by z divided by r. So let me write this r as the square root of z conjugate. To get that, this will be minus I, the derivative with respect to z of, we can cancel, right, the z with the square root of z to get the square root of z divided by the square root of z conjugate, like this, and then divided by z divided by r. Perfect. So this is a minus I. And what will that be? We have 1 over the square root of z conjugate, and then 1/2 z to the negative 1/2, right? So we can write this as 2 the square root of z conjugate times z, right? Okay, perfect. So this is divided by z over r, which is the square root of z conjugate z. So if we simplify, we can cancel these elements to get that this is, well, minus I divided by 2z. Perfect. And recall that this is the derivative of theta with respect to z. Perfect. So now we are going to keep going with the r, right? So we need to calculate the derivative of r with respect to z. And what would that be? Well, we have the square root of z conjugate. Recall that I'm using this expression over here. So this will be 1/2 z to the negative 1/2, right? So this will be the square root of z conjugate divided by 2, the square root of z, and then we multiply by maybe the square root of z conjugate here and here to get that. Well, this will be z conjugate divided by 2r, right? Recall that r is the square root of z times z conjugate. So this is the derivative of r with respect to z. Okay, perfect. So other thing that we are going to use is the Cauchy-Riemann equations in polar coordinates, right? Recall that this expression for the derivative of f, well, it has derivatives with respect to r and with respect to theta. We're going to be interested in showing an expression, but that only depends on the derivative with respect to only one variable, r or theta, right? So we know that to change, to change the derivative, for example, from theta to r, we can use the Cauchy-Riemann equations, right? We have seen in a previous lesson that, well, the Cauchy-Riemann equations in polar coordinates are these over two that I have here. So again, if we have in the derivative of f derivative with respect to theta, but we want to get an expression of only derivatives with respect to r, well, we can substitute this value with this other one, right, to only get derivatives with respect to r. So that is what we are going to do. So let me bring back the Cauchy-Riemann equations here. Okay, perfect. There they are. And then, well, we are going to start to substitute on the derivative of f with respect to z. Okay, so the derivative of f with respect to z will be the derivative of u with respect to r, and then the derivative of r with respect to z, which is this. So it is z conjugate divided by 2r plus the derivative of u with respect to theta, but that is this. So we have minus r, the derivative of b with respect to r, and then the derivative of theta with respect to z, and which is this. So it is minus I divided by 2z, and then plus I times the derivative of b with respect to r, and the derivative of r with respect to z, which is z conjugate divided by 2r. Perfect. And then plus the derivative of b with respect to theta. So from this equation, we have that the derivative of b with respect to theta is equal to r, the derivative of u with respect to r, right? So this will be r, the derivative of u with respect to r, and then times the derivative of theta with respect to z. So that is minus I divided by 2z, like this. Perfect. So we just need to simplify this expression. And well, we notice that there are variables like z and z conjugate that are intruding maybe the answer that we need. So we still need to change that, right? But we know easily that z is equal to r e I theta, and that z conjugate is equal to r e to the negative I theta. So just by using these definitions, well, we are going to get what we want. So the derivative of f with respect to z is equal to the derivative of u with respect to r, and then z conjugate, which is r e to the negative I theta divided by 2r, and then plus I r divided by 2z. z, which is r e to the I theta, times the derivative of b with respect to r, plus I, and then the derivative of b with respect to r, z conjugate, which is r e to the negative I theta divided by 2r, minus I r divided by 2 r e I theta, the derivative of u with respect to r. Perfect. So we are also going to be interested in showing this as the real part plus I times the imaginary part, right? So we are going to separate both quantities to get the next. And we are going to simplify, of course. So the derivative of f with respect to z will be the derivative of u with respect to r, e to the negative I theta divided by 2. And then looking at this quantity is going to be real when we multiply by this I, we are going to get actually a plus, and then r cancels with this to get that e to the negative I theta divided by 2, and then the derivative of u with respect to r. Recall that I'm taking this e to the I theta to the numerator just by taking the minus sign at the exponent. Okay, so then we can factor an I, cancel these r's, take this into the numerator, we cancel these r's, and then we have plus I e to the negative I theta divided by 2, the derivative of b with respect to r, plus e to the negative I theta over 2, the derivative of v with respect to r. So as you can see, we have exactly the same quantities, right? So we can sum them to simplify a little bit more to get that our final result will be that the derivative of f with respect to c is equal to e to the negative I theta that multiplies the derivative of u with respect to r plus I, the derivative of v with respect to r. So yeah, I think this is already an important result, a first important result, because recall that by using the Cauchy-Riemann equations, we still can transform this equation for an equation of derivatives with respect to theta, right? So we are going to use these relations to get that the derivative of f with respect to z is equal to e to the negative I theta that multiplies the derivative of u with respect to r, but that is 1 divided by r, the derivative of b with respect to theta, and then plus I, the derivative of v with respect to r, but that is minus 1 divided by r, the derivative of u with respect to theta, like this. And just if we simplify a little bit more to get the common factor 1 divided by r out, we get e to the negative I theta divided by r that multiplies the derivative of b with respect to theta plus minus I, the derivative of u with respect to theta. Okay, I think that's the second final result of the video, which is the derivative of f with respect to z. As you can see, these two things are exactly the same, but they are just expressed in terms of derivatives with respect to a different variable, right? Okay, so I think this was the goal of the video, and thank you so much for watching.